Okay, ladies and gentlemen, welcome to the first talk in the Geology lecture series this year. Good news is we have at least the 3 to match last year. Bad news is I don't have the next poster available yet for all of you to take out and then put out in January. If you keep your fingers crossed, you may have heard of a guy named Chris Goldfinger. He's been doing a lot of the really amazing, frightening, scary earthquake work off of the Oregon coast. And so with any luck on January 28th, he'll be standing here on a dark and stormy night just after the anniversary of the last great Cascadia earthquake. If you go to www.socc.edu and find the Geology Department website, you can find the Geology lecture series, and you'll be able to track down if and when Chris is actually coming down here, and you can also find out when the other dates are, which include March 5th, which is a Saturday, Carolyn Dreiger talking about earthquakes and destruction. Also June 4th, researcher from Penn State that's coming out that's been part of the ocean drilling program, also to talk about earthquakes, and hopefully one other mystery date to be announced later. So I'd like to take a moment to thank our sponsors. One is definitely the college for providing the space and also the technical support, and also the amazing ability to web stream out into the broader world, especially those folks down around Gold Beach and Brookings. Also the college's foundation, also Oregon Resources Corporation, one of our sponsors, and also National Association of Geoscience Teachers. I got a grant that's still kind of kicking around for a little bit. So it's my pleasure this evening to introduce to you Dr. Vicki McConnell. And Vicki is the state geologist and also in that serves as the director of DOGAMI, or the Oregon Department of Geology and Mineral Industries. She has a broad and varied background, starting in Denver, and I'm thinking you're going to want this microphone instead. Is that what I'm, yeah. She got her PhD from the University of Alaska. She's worked in a variety of private and public places prior to going to Baker City as for DOGAMI as a field mapper, and currently, as I mentioned, as the state geologist. My pleasure to introduce to you this evening, Vicki McConnell.
Well, thank you, everyone. I really appreciate it. And to kick this off and get started, first of all, I'm very honored to have been asked to come and do a presentation here. And I didn't realize it was the inaugural presentation for this series this time, so thank you again for that. That's quite wonderful. And so I want to thank Ron, and I want to thank the community college, and this is a great turnout and a beautiful venue here. And I want to thank all of you for taking the time from your busy schedules and everything else that you have doing on a dark and stormy night and coming out to hopefully be enlightened on some of the information about the great geology in this state and how that affects you in your days in your daily in and outs. And I also, before I forget, I want to actually make sure that I thank my staff, who helped me very much with putting all the information together with this. And even though I actually made it my very own self with PowerPoint, it was borrowing heavily from everyone else's slides and data and information. So big thank you to all of them for their patience with me on this. And again, as Ron said, in a case I'm sure you all are pretty familiar with, I am the director of the State Department of Geology and Mineral Industries. We're a small state agency. Our mission is to develop geologic information for the health and prosperity and information for the state. And we have a whole variety of submissions within that. And what I'd like to do today, usually when you're hearing us talk about things, it's about hazards. We've been doing a lot about that. Actually, a lot of times I feel like my name is Dr. Doom. But right now, I want to talk about something a little different than hazards tonight. So what I really want to do is I get the opportunity to share with you folks tonight is actually to kind of build Oregon from the ground up. And in doing that, and in building it from the ground up, to share with you some of the interesting facts about the mineral and energy resources in the state, the history of how those resources have been both for exploration and development, and then kind of look into the future as we're looking at what are some of the ideas and what are some of the areas that might be of interest for both minerals and for energy. And I'm going to guarantee you that there's not a single, particularly with energy, renewable or otherwise, that I'm not going to be able to relate back to the geology in one way or another. So here we go. So it all starts with the geology, and with geology, it all means patterns. Whenever you're looking at the geology of anything, and what we're looking at here is a generalized geologic map of Oregon. This was developed a couple of years ago from what we call our Oregon Digital Geologic Map compilation. So this is a compilation and distillation of the best geologic data and information that's out there that have been put together into an online server. And one thing I should mention right off the bat, if you go to OregonGeology.org, you can at any time get onto any of our interactive maps and look and download any of this information and data that I'll be talking about today. So if you really want to cruise in and have a look at that, I would be honored if you would. So I say patterns. So what do we look at? When we map the geology, what we're doing are putting together, distilling that information into those geologic stratigraphies or lithologies, the type of rocks or something that are similar to each other. And so immediately what comes out when you look at a general map like this is you start seeing colors equal similarities. So you start seeing patterns that start occurring where you have the same type of rocks. Well, why do we have them? Why do we have the same type of rocks there? And what do those mean about to the bigger meaning of where you may have a mineral or an energy resource? So if you overlay over, let's just take this simple overlay right here. This is from our what's called our mineral information layer of Oregon. All of those red dots represent a spot where some type of mining has taken place in the state over, this is a snapshot across space and time. So many of these are not active anymore, but it's in the database. So all I did was take the space and time, take a snapshot, and overlay it over that patterns. And you don't see a whole lot right away. You do see areas where it seems like there's clusters, where it seems like there's more activity that may have gone on in others. Now, that could be because there's more people there, or it could be because the geology is the controlling factor. So let's do a little more. Let's parse this out. Let's kind of look at this if we take a little bit, step back and take a little bit more information on this. So now let's look at it this way. Let's take that same map, those same dots, and let's pull them apart into some of the information about actually the type of mining that was going on at any one time. And all I've done here is I've separated them into 4 main groups. And as you can see, number 1 is aggregate. That's sand and gravel. That's upland quarry rock. That's the kind of rock you see on gravel pits all over the place. And this, again, this is through space and time, so not every single one of those is an active gravel pit right now, but at some time, someone was probably excavating some rock there for some reason. And you can see it kind of, it's a background across all the state. And we'll talk a little bit more about why that is there. You probably have some ideas already. You can look at something like industrial minerals. Industrial minerals are kind of a catch-all term for a whole variety of not very sexy stuff to talk about when you're mining, but you use it every single day of your life, and it's quite important. And I'll go through a list of those with you later. And as you see, they're pretty much scattered all over the place, too. And there's a reason for that. We'll look back at that. Then you can look at something, Then you look at something like coal. And lo and behold, we actually have coal in this state, and we actually have had coal mining. And if you look for those little black dots, you'll see that down here by where you folks live, there's a whole variety. And then there's a kind of few dots that kind of go up through the center of the state here. Well, there's a geologic reason for that. And as we build Oregon, we're going to see what that reason is. And then finally, we have metals. And in this case, metals means both industrial metals and precious metals. So you're talking gold and copper and iron and silver and all of the metals that you would do if you were doing some type of hard rock mining. And as you can see, those cluster very strongly in the northeast and the southwest part of the state. And there's definitely a reason for that, too. So, if you thought you were going to get out of a geology talk without hearing about plate tectonics, then I'm sorry to disappoint you, but that's where it all starts. And so even if we're talking about mining and minerals and energy, where we have to start is talking about plate tectonics, which is really the geologic engine that drives everything that we see on the face of the earth, on the continental and the ocean side. And for probably everyone has heard of plate tectonics at least once, so I won't bore you with all the details, but let's go into a little bit of it here. You know that we have a subduction zone off the Oregon coast. You folks are probably very sensitive and aware about that. You hear about it a lot. It has a lot of activity. It means that you have this continental or this ocean crust that's smacking up against the North American plate, and when you do that, something has to lose. One has to go down and one stays up. And in this case, because oceanic crust is colder, it generally sinks. It's denser, so it starts to sink below the continental crust. So you have a subduction zone, and along with that comes a lot of activity, including earthquakes and including volcanoes. And that's a given. Where you have a subduction zone, you're going to have earthquakes and you're going to have volcanoes. Now, there are energies. There's other things besides hazards that are associated with earthquakes and volcanoes, and that's actually what I'm going to be talking about. You also have areas where the crust is actually where we're forming new crust. If it's out in the ocean, it's called spreading centers. If it's in the continent, then they're called rift zones. We have both of those that have occurred in Oregon over the past, and we're going to look at how those have affected some of the mineral and energy resources we have, that we have. And we're even, and you're going to see in a minute, we're even the proud owners of something called exotic terrains or island arcs that used to be somewhere else, and they're now owned by Oregon. So keep all of this in mind, because we're going to be looking at every single one of these again as we go through the history of Oregon. So let's step back in time now and look at another snapshot. And this is around 140 million, 150 million years ago. This is in what's called the early Cretaceous. And at that time, and you can see some of the shapes that look kind of familiar to what we see now. At that time, we were looking at the breakup of one of these supercontinents. And what we had was a huge Paleo-Pacific Ocean and a huge single continental plate that finally just couldn't take it any longer and decided that it needed to start splitting up. And so what we started with, and I want to point a few things out to you because in a minute we're going to focus in Oregon. But this was the beginning. What we start seeing here are those rift zones I was talking about. That's that divergent marine or ocean rift zone. And so this is the beginning of the formation of the Atlantic Ocean. It starts splitting. Here's the North American plate. You can see the east side in the middle part and even up into British Columbia and that area. That's the stable, what we call the Cretonic plate of North America. That stuff has been around for a very long time, and it keeps floating around as that plate runs into other plates and then gets separated from it. You can see here's the African plate, and it's just starting to separate from South America, and South America will be wandering over here, and then we'll have the formation of the volcanoes that turn it into Central America. Here's the subcontinent of India. It's just splitting off from Antarctica and Australia, and it's going to make a long journey up here and eventually end up on the Eurasian plate here, into what we call slamming into the Eurasian plate and forming the Himalayas. So let's take a little close-up now about what's going on here in North America. So if you look a little closer on the North American plate, you'll see again that the east is pretty well formed, recognizable. The west is recognizable. You can see where Canada is and everything. But if you look over here about where Oregon and California and even Alaska and everything, there's not a lot recognizable there. And that's because even starting about this time, what we had is the North American plate ended at about Idaho and Colorado. And everything beyond that was marine. There really wasn't a continent. There wasn't an Oregon. There wasn't anything there except the marine part. And what we were finding as these plates started splitting up that these island arcs started moving across, subducting onto the edge, and gluing themselves or suturing themselves onto the edge of the North American plate, and actually forming what we now know as California, Washington, Oregon, and much of Alaska. And we call those exotic terrains. And they're actually a series of volcanic arcs. Remember, I was talking about that we say we even own volcanic arcs here, and reefs that were associated with them. And a volcanic arc and a reef is really a modern analogy of that would be the Indonesian island, the whole archipelagos of the Indonesian islands. A whole series of volcanoes and islands and reefs that are all formed, and as they are on their plate, if that plate starts wandering across, in this case the Pacific, when it runs into something like the North American plate, it will, as we call it again in geologic time, slam into each other at the rate of about 4 or 5 millimeters a year, and eventually suture itself onto that, that plate. And so what we have done then is now recall somewhere over here is where the North American plate is. So this is, the light green shows the really kind of the total amount of material in these whole series of these volcanic arcs that hit against the North American plate and then suture themselves or stuck on there. And we have a whole series, and it starts over here. There's the Wallowa terrain and the Baker terrain and the Old Ferries terrain, and then you move down here into the Klamath and a whole series of terrains here. And then in between, underpinning everything that we see at the surface now, are the rest, really kind of the remainder of these rocks. They're exotic. They belong to Oregon now because it's what makes up Oregon, but they're not part of, they were never really a part of the North American plate until this activity happened. And where we see them exhumed or at the surface then is in the northeast and the southwest. Now, as these marine sediments and these volcanic arcs, as they did this slamming activity, they were changed, they were metamorphosed, there was a considerable amount of heat and pressure, a lot of that material got subducted underneath and then came up and reappeared as batholiths and plutons. So in the same area and a little younger, but coincident with it from 165 to 130 million years ago, you had in these same areas a tremendous amount of subduction zone volcanic activity that was occurring with these old subduction zone activities. Since then, all that volcanic, all the what we call the extrusive volcanics, the lava and the pyroclastic flows and the volcanoes and all of that have long since eroded away. And what we are left with are the cores of those big magma chambers, and that's what forms the granites and the granitoids and all the granite rocks that we see both in, if you've ever been over to the Wallowa Mountains and see it's all granite in there, and it's same in the cores in the Klamath and in the southwest. And this is really part of the glue. This is part of really what stuck all of those island arcs together and formed what is now underpinning most of what is now Oregon. And in these, you have a lot of hydrothermal activity. You have very hot reactive fluids that are moving up through veins in all of this and in the dikes. And within those, you have these concentrates of gold and silver and copper, nickel, arsenic, and mercury. So those are what miners or people that are looking for hard rock concentrations are looking for, is in these type of rocks. And then around, so they're cored in that, and then they're also contained within those metamorphic rocks that make up those exotic terrains. So now let's go back and look at what that mineral information was. If we look at those dots and kind of parse them out a little bit more, then what we have here is this is occurrences of prospects in mines when we're talking about hard rock. So again, those metals, either the precious or the industrial metals, and where the mining has occurred over time. And looky here, what do we have? We have those concentrations in exactly the spots that we have the exhumed exotic terrains and these cored granitoid and granite rocks that made up the big magma chambers. And that's exactly where you would find it. That is a type locality of where you would be looking for precious metals and industrial metals. And here we've kind of pulled them out into certain things. There's areas where there's mercury and antimony and arsenic sites, and you know, as much as those things sound awful, people do and have mined them in the past, and we do have uses for them still. Copper, lead, and zinc sites, aluminum, chromium, nickel, and iron sites, and you can see they're kind of cored around both these areas, and there's quite a concentration of those in the serpentinites that you have down here. And then the gold and silver sites. And you can see, again, that's in that core, in those granitoid areas, in the cores of the mountains is where you're finding that. Now, presently, today, in the state, we do not have what we would consider a hard rock mine, which means there's actually someone going out there and digging a mine and forming an adit and following a vein and pulling it out, pulling the ore out, and then doing some type of extraction or milling of that ore so that you could then concentrate whatever you were looking for, be it gold, silver, etc. All the mining that is occurring right now is occurring in what's called placer deposits. And what placer deposits are is when you have the, you know, what happens whenever you have a mountain range in water? Well, everything that's high starts getting eroded down, because the whole idea in geology is to form an equilibrium where the high stuff becomes the low stuff. And in this case, when you're looking at materials that are called heavy metals, when you start eroding those, whether you're eroding them into cobbles or you're eroding them into sand or you're eroding them into silt or whatever, generally the heavy stuff doesn't go that far. The lighter stuff moves on out of the system. The heavy stuff tends to sink out and separate itself out. That's your first simplest way of concentrating your heavy materials or your heavy metals. And that's why you see people placer mining, which means they're dredging up either in placer mining, which you can do it in the riverine, or you can look for the old terraces, the old river terraces, etc. And they're going through that and they're pulling that out and they're reconcentrating where those heavy metals have already separated themselves based on the fact that they're heavier than the lighter stuff in the system. And that's what we find now. Almost all of the mining that was going on both in the Northeast and in the Southwest, when it comes to particularly looking for precious metals, are placer mining. Now we do have, and I guess just to add a little bit to this, is that both these areas in the really early settling of the state, this was the economic drivers. Mining in these two areas, particularly for silver and gold, were the economic drivers for those part of the state at that time. That really is why we have Baker City and why we have LeGrand and why we have Enterprise and why there's still Grants Pass and Jacksonville. I mean, that is the reason that they were built, is that they were boom towns for the mining activity that was occurring at the time. And I just said, what is the current activity? So part of it is placer mining for gold. We do have one other interesting activity that is getting ready to start up in this area. And you guys notice you've got a lot of stuff going on down here. You've got the gold and you've got the chromium, and you're going to have a few other things here in a minute I'm going to show you. But here in Coos Bay, in an area here, you have some terrace sand deposits that, again, have concentrated some of those heavy minerals and heavy metals that are coming out of the mountains. And the three primary ones are chromite, garnet, and a zircon, kyanite, and starnite blend. Chromite is of interest to the foundry. It's called foundry grade, and it's of interest to iron and steel making. It is part of what is used for developing the molds in the foundry for it. Garnet is an abrasive. It's also a pretty rock that is a semi-precious stone, but it's basically abrasive, and it's used from everything from sandpaper to fingernail files, but it's used a lot. And then these three rocks are relatively rich in aluminum, and they're used for refractory. And that means, refractory means they don't melt easily. So again, they're used in iron and steel alloy making. And so what has been found is that there are terraces, again, and there's two ideas about where these terrace sands are. They're either old marine sands, where this used to be where the coastline was, and these sands are your basic heavy sands that you see on the beach when you walk down, or these may be delta sands from old river systems. But you have quite a concentration of these heavy minerals that have come out of the mountains in this area, enough that there are entities that feel that it makes it economic to mine these areas. And that is something that's coming up on the forefront here pretty soon. Okay, let's go back and have a look in time again. We've actually built, whoops, don't want those guys to show up yet. We've actually built Oregon here. Remember, we've got our exotic terrains and we've got our batholiths. So that means now that the coastline is no longer over here somewhere. Here's the old coastline about 130 to 50 million years ago. So that's where the coastline would have been for Oregon. That was the total amount of Oregon at that time. And what you find then is typically, as in any coastlines, you're building up a bunch of coastal and marine sediments. It's going to be full of swampy muds and silts. It's going to be full of sandstones. And in this case, this was occurring in the Cretaceous, in the age of the dinosaurs. This was a relatively warm, global warming time for the whole Earth. And so we had a lot of flora and a lot of fauna. It was a big, swampy, messy area everywhere. And so we find evidence of Ichthyosaurus here and ammonites, and we have beautiful fossils that have been pulled out of Oregon of all these. And the Ichthyosaur is not quite, it's an ancient fish-like animal, but it's not a dinosaur. We're yet to actually find dinosaur bones here, although we do have these sediments that are of the right time. Lots of swampy. It was a time when there was a lot of peaty and swampy and estuaries going on. And in this area that we were on the Old Coast, we were actually getting a lot of what eventually even formed those coal beds that we were looking at earlier. So within this area, you have a lot of other material, but you also had coal forming. And if we go back and look at where we are now, and you look along this area right here, then what you see is the outline of those old ancient Oregon coastline and the coastal deposits. And you can follow that as you follow these coal deposits. Now, some of you are probably familiar, but in this area, this is where the highest concentration of coal is. It's in the Coalbed Formation, and it's exposed at the surface, and there's actually been coal mining that's gone on here for several decades. And it was used primarily as a fuel, coal fuel. Many people burned coal in days past. And so it was mined and used locally as a coal fuel. Lately, these coals and this coal area has come under interest for a secondary fuel that is, or energy that is trapped in coal, and that is, and here's kind of the outline of the Coalbed Formation. As you look at, there's Coquille, there's North Bend and Coos Bay. So you've got coal all through here, and there's actually still old adits you can see all around this area where they were mining the coal. What we find now is that there's a lot of interest in harvesting the gas, and it's natural gas, methane gas in particular, that occurs with coal. And as an extreme example of that, and one that was really tragic, if you remember what happened with the terrible coal mine explosion in West Virginia this summer, that was because of methane gas that had collected within the coal mine and wasn't being, but they think was not being properly exhausted out and built up, and there was an explosion that caused. So we've known for many, many years that methane occurs with coal. And in most cases, what everyone wanted to do was to get rid of the methane because they were only interested as the coal, particularly as a fuel and nowadays as an energy source. But methane has now become a little bit more popular than coal in many places. And so we do have this interest in harvesting that gas from the coal, and it's called Coalbed Methane Extraction. And the way that it occurs is, instead of going down and mining out the coal, you actually drill wells down to your coal bed. And what you want to do is, you have to have two things that occur within anything. And actually, just to back up and say, anytime you want to take something out of a solid rock, you have to have two processes that occur. And there are things in solid rock that can come out. Water, I mean, that's how you have aquifers. Gas, oil. I'm just going to jump ahead and I'll come back to this. But you have to have two things that occur. Number one, you have to have pores, or you have to have holes or voids in that rock where other things can collect, whether it be water, gas, oil, etc. And that's fine. So you have to have pores. The other thing you have to have is some type of permeability. Those pores have to be connected somehow. Otherwise, they just stay there. They're separated. They're isolated. You cannot recover whatever is in it. So you have to have both of those processes going on. You have to have porosity, where you can collect the material, and you have to have permeability so you can get it out of this particular rock. And so in coal, what we have for the permeability are actually kind of squarish cracks that occur all through the coal. And if you've seen coal, you notice it kind of has a squarish look to it. And as you get higher and higher in grade, it gets more and more square. And they're called cleats. So if we go back to this new thing about harvesting the gas out of the coal, what is really necessary is to make sure that you have enough of these cleats to be able to get everything up, get the gas and the water out of the system. So what it frequently happens is that you'll drill lots of wells, but you'll also enhance your cleats by injecting something back into the well to open those permeability up. And it could be water, could be inert gas like nitrogen. Whatever it was, is you want something that's going to drive the methane out. And remember, gases, oil and gas, are lighter than water. So if you get the water out of the system, then the gas is going to follow along. Now, there was work that was occurring down here with what's called coalbed methane, again, looking at that coal source that was here in the Colita Formation. And there were several wells that were drilled, and they did find gas, and they did find water, and it's frankly, I think it's not economically feasible for them right now to go into development mode. So the resources there probably not at the level that they thought it was, and so it has not gone forward into production mode at this point. Couple things to think about and remember about coal. U.S. has got a lot of coal. We're the Saudi Arabia of coal. We've got it. That means it's being used, and it will continue to be used because it is a resource that we have. Looking at gas in the coal is a way to get out a relatively pure fossil gas. Methane is pure compared to some of the other gases. It doesn't have a lot of other stuff with it that makes it that you have to separate out, like sulfurs, etc. You don't need structural traps, and I'll explain what that is here in a minute, but you do need those cleats. You do have to make the permeability if it's not there. Some of the disadvantages, it's still a fossil carbon, so there's still a carbon footprint that goes along with the gas. It's not as high as the coal, but it's still there. You have a lot of water that can come out of this, and this water can be pretty nasty, and it has to be treated before it can be discharged, so you just can't run it off. In an ideal system, the water that came out would go back in to help with your porosity, but it doesn't always work that way. Generally what you end up with is more water than you can put back into the system, and then somehow it has to be treated and disposed of. And you may need a whole lot of holes to make this work in the areas. And again, what we have here are relatively small, discrete basins with relatively small amounts of this. If you compare to what's happening, for example, in the Wind River Basin in Wyoming, this is really small stuff. Okay, so we're up to about 50 million years ago, and we've been building this coastline. Remember, we put on the exotic terrains. We started building our coastline here, our older coastline, and we're slowly keep building our coastline forward until we get to what we have now, which is our existing coast range sediments, our coastal and marine sediments. So we're getting pretty close to the present time. Those have been building up and around for about 50 million years. Again, a whole series of stuff you would think as they're coming off the high grain and the high land and going into both the lowlands and on into marine sediments. So it's sandstone, siltstone, shale, limestone, all the both coastal and marine sediments that have been accumulating. And this is the perfect kind of permeable type of sedimentary rocks that could actually be what we call traps for oil and gas. And so before I tell you exactly what that is, let's go on, let's talk a little bit more about the coast. I want to remind you that here's our Oregon coast. This is a map. Here's the present-day Oregon coast. Here we are down in here. That's looking at the coastline, and it's looking all the way out. This is really what's the continental shelf along here before we kind of go into the deep water. And there's a red line there, a thin red line that outlines where the subduction zone fault is. And what I'd like to remind you is that a coastline doesn't stay locked in place. As you've seen it, it's already been migrating across through the tens of millions of years. Well, even in the very short times, coastlines go back and forth, and they go back and forth depending on a lot of things, but primarily whatever the climate is at the time. And so, for example, our coastline 21,000 years ago, which was at the time of the latest glacial maximum, so that's when we're in an interglacial right now. We're actually in a warm time between glacial activity. In the last interglacial maximum, which means when we had the most of the water, the marine water locked up into big continental ice shelves, our coastline was actually about 20 miles further out and about 400 meters shallower than it is now. So all of this is actually considered part of our modern coastline as well. So right now, as we have melted all that glacial ice, we keep moving further and further in. And depending, that coast will really depend on what the overall climate is at the time. So it migrates back and forth depending on what the climate is and what the water, where the sea level, where mean sea level is. Remember, we've got plates converging. So these sediments in here are not just staying in nice horizontal layers. They're actually being rapidly deformed, and they're being uplifted, and that's where we get the Coast Range. The Coast Range are primarily all these mudstones and sandstones and everything that were formed many, many years ago, many millions of years ago, and they're now being very deformed. And so we have a small potential for gas, both onshore and offshore. So now I just wanted to mention a little bit about what these structural traps are that I mentioned earlier. And what it is, again, is taking what were horizontal sedimentary rocks and deforming them in a whole variety of ways. And it's squeezing them up so that they squeeze and become anticlines and synclines, faulting them and then pinching them off, a whole variety of things, tilting them on their sides. And what that does then is it creates areas, high areas, where you get water collecting and then you get oil and gas on top of that. Those are the traps that you look for if you're in the petroleum industry. You look for those marine sedimentary rocks that are quite thick and have the potential for being deformed, because that's where you find your trapped oil and gas. And so it goes, water, oil, gas. And that's separated out just the same as if you take your water and pour your olive oil on top of it, and then I'm afraid what gas you'd want to put on it, maybe nitrogen. But it's the same idea. Water is heavier than oil, so it always floats to the top. So this is what you look for. So, yep, that's what we have here. We have that potential. So if we look about where there has been activity for gas and oil exploration in the state, let's go back and see if we see those patterns still holding true. And yep, we do. We have two areas where they've been really looked at. We have a little bit of minor work that's going on out here. And remember, that's where that's where our older coastline was. And we have a big concentration of oil and gas exploration that's occurred in our present-day coastal range sediments, including a couple of wells that were drilled back in the 60s offshore, of which were pretty piddling, and they found a little bit of gas and not worth anyone's trouble, and no one's come back to look again, and I don't really expect them to. But just to say, we know that it's there, and we know we have the right kind of sediments and et cetera for it. What you do see, though, is concentrations here, and what we're looking at here are where we have had permit applications for exploratory or development drilling for oil and gas, again, through the years, starting in the 50s up till now. So you see there's a concentration up here in the northwest part and down here in the Coos Bay area. So if we go up and look at the northwest part of it in Columbia County, and here we are, there's Clatskanie there, and St. Helens is down here. So there's the Columbia River. So this area right here in the highly deformed and faulted Coast Range forms an ideal structural trap. And yes, there was gas involved. We've never found any oil, but they did find natural gas. So this is the mist gas field. This area has been producing gas since the 1970s. It doesn't produce a lot, but it is our one and only actual gas field in the state. Presently, we have about 80 wells that are permitted. A third of those are permitted for actual production of new gas. A third are permitted for injection of water or something back in the system to do reservoir enhancement. And a third are for storage from gas that being piped down from Canada. So those are reservoirs that are now empty, and so they're using that reservoir to store gas in. And there is a little bit of activity down here. The only activity lately has been those Coalbed methane wells. Okay, so what about other energy sources besides fossil fuels? And we have a big interest now in renewable energies in the state, renewable types. And so let's go and see what do we have that's available for renewable energy then. Well, let's go back to our patterns. This time let's pick up at about 15 million years ago and get into the stuff I really like, all the volcanic activity. And so remember I said we've had a rift zone. We actually have evidence of what we call rift volcanics, continental rift. In other words, this part, the southeast part of the state, and if you've ever been over there, you'll notice that it looks really different than the rest of the state, and that's because it is really different. It is much more similar to Nevada and Arizona and New Mexico, and it's not just because it's hot and dry, but it's also because of these rifts. All these extension and volcanics have formed what's called the Basin and Range. And this is the furthest northern part of the Basin and Range. Very similar to what you see if you go to Canyonlands or anywhere like that. You get these big, deep faults, normal faults. Part of it falls down, and you get a big basin, and then part of it goes up, and you have a big mountain range next to it. And it's all the volcanic, massive amount of volcanic activity over those 10 to 15 million years. And this is all due to older subduction and the rifting that was going on. That leaves latent heat. Remember that. We also have our good old high cascade volcanoes, because remember, we still have an active subduction zone over here, and where you have subduction, if you remember in it, when you get down, if you're looking in cross-section, when you get down to about 40 kilometers deep, what starts happening with that plate is it starts melting, or sweating, we like to call it. And so there's materials that start melting off. They form magmas, and it's called diapiric rise, and all it is what happens is a big blob of it starts working its way up through that cold continental crust. And that's what forms your volcanic centers. And so where we can see that we have a nice north-south subduction zone over here, because we have a nice north-south volcanic range that's showing us exactly where about 40 kilometers deep is, where that slab is going down. And remember, it doesn't stop here at the border. It actually goes down all the way down to Lassen and all the way up to British Columbia. And that outlines. Now, where you have active volcanic activity, and our youngest volcanic eruption in Oregon was 220 years ago. And we know Mount St. Helens just erupted just in 2004. So we have plenty of heat here. As a matter of fact, if you look at what the geothermal heat flow is for the United States, you'll see, you'll see that Oregon has it both looking at that rift volcanics and looking at the Cascade volcanoes. And it's quite high. It gets up in those are milliwatts per meter square. So it's some of the highest heat potential in the United States. Therefore, we've had a lot of renewed interest in geothermal production here in the state, since we now have a renewable portfolio, that these companies can actually sell their energy production now to some of the big energy producers. So we have 6 areas that are actively researching for geothermal This place here, Neal Hot Springs, will probably go online with a plant next year. OIT has actually gone online with a low-temperature plant where they have gone off the grid and they're creating their own energy at OIT through low-temperature wells they have there. We also have research in the Newberry area on something called enhanced geothermal systems. And this is where you dig very deep, 10,000 plus feet deep, and you don't worry as to whether you have water in the system or not. You're just looking for the highest heat you can get, and then you introduce water into the system. And that research is going on now. And then what else do we have for renewables? There's wind, and there's sun, and there's waves, and there's dams, and there's hydroelectric, and there's all kinds of things out there that make up the full package. I like to call dams kind of our conventional renewable energy. That's certainly where we've had and what we use as the most for creating the energy that we have, our electricity in this state, and it's why we get it so cheap, because we have the dams and the hydrothermal. And the hydroelectric. What's been built around that, what these red are the major transmission lines for moving that electricity from where it's being generated to where someone wants to use it. And that's probably the biggest problem that we're going to have with getting some of our renewables online with where we need it, because there are whole areas where there's no transmissivity, but there's high potential for wind and geothermal. Wind farms, right now, most of our active wind farms are here along the Columbia Plateau and the Columbia Gorge, but the potential is very high everywhere in the east part of the state. But remember, there's not a lot of transmission lines over there, so there's going to be a real struggle with that. Now, I told you I was going to explain how all of our renewable energies are related to geology. Well, if you notice, there's nowhere on the west side that anyone has any potential for wind energy. But we have wind over here. It's just we got a bunch of pesky trees that are in the way of the wind. What you see on the east side of the state are areas, broad plateaus, where we really don't have a lot of vegetation. We have a lot of wind, and it's very dry. And the reason that is because of the rain shadow from the Cascades, from the geology. That's what makes the east side of the state so different climatically from the west side. It's all about the geology. Solar so far is really, even though we have a high solar potential on the east side, we're not looking at commercial development right now. Primarily what we look at are individual houses and businesses that are looking at developing solar, and that's both on the east and west side. One of the areas that's probably the most interesting for potential new renewable energy is wave energy. And that's certainly something they're not going to have on the east side. It's going to be your guys' only. And that's looking at, there's already a site that, there's a Reedsport Wave Energy Park that has been permitted and will probably be putting the first of their buoys. And this is an example of one of their buoys in the water next year, and they're looking at having something online for actual commercial within the next, I would say, a decade. They're saying 5 years, but I think there's a lot of research that'll have to go along with wave energy at this point. Now, lest I forget, I wanted to go back just quickly and remind everyone about what I call the other but necessary minerals that are out there. And that's really looking at quarry, sand and gravel, and those industrial minerals, and the way that they're kind of shotgunning across the state. First, sand and gravel, which are in the floodplains and the rivers, and then the quarry rocks are in the uplands, and that's what all these blue are. That is by far the most mined material in the state, and it's the most basic. You can't do anything if you don't have quarry rock. You can't build a road, you can't build a house, you can't build anything if you don't have quarry rock. And you either have two choices. You could either, and this is why you find that there's so many dots all over the place, is where people are building things, they want to look for that resource nearby. It's expensive to truck it from somewhere else. So that's why you see this shotgun, and particularly the clusters in the area where we have more population. Industrial minerals cover a whole bunch of things. Everything from pumice to clay to diatomite, quartz, zeolites, everything here. And all of those things are used in a whole variety of things. Everything from kitty litter to filtering beer to to making your blue jeans looking like they're stone-washed. Well, you use pumice to do that. So there's a whole variety of uses for industrial minerals. And so we find that we always have a call for those. And we have quite a few in the state. And I could give a whole talk on just explaining all the different industrial minerals, but I won't bore you. And then, of course, I couldn't resist just putting up, we do have a small business in the state looking at some of our semi-precious stones and rocks. And here we're looking at sunstone, which is our state mineral, or excuse me, our state gem, and thunder eggs, which is our state rock. So kind of to finish up, then what are we looking at? I've kind of said what the future possibly is for energy, and that's wave energy and solar and looking at wind and everything. So what is it for mining in the state? What is it that maybe is possibly out there? Well, we have two areas that have a lot of interest right now, and we do have some resources. And one's rare earth elements. This is a series on the periodic table of 17 elements that don't occur very often in high concentrations. They have very interesting properties, and they occur in very exotic intrusive and extrusive rocks. And we do have some carbonatites and monazites in southeast Oregon. And so I am kind of forecasting that there'll be some interest in at least exploration for those type of materials in the next few years. And uranium. And again, uranium is kind of an old thing. There was an intense amount of exploration and mining for uranium in the 1950s. And then it kind of fell off as there was less interest in actually having nuclear reactors. But right now, on the east side, in the eastern United States, there are 50 applications in for either developing new nuclear reactors or enhancing the ones that are already on site for energy development. So there's going to be a big interest in the materials, in the uranium, to actually fuel those. And again, those occur in southeast Oregon. So I think that's it. So that's where we were, that's where we are, and that's where we might be. And that's how we built Oregon. And thank you very much.
So we'll take time for a couple of questions. And also, in the event that you didn't sign in on your way in, if you could take a moment on your way out and sign in, including your birth date, so we can send you a birthday card.
What's the state position on fracking in the area? Anybody put any permits for it?
Good question. Hydrofracking or fracking, it's really dependent on what you were going to do it for. And in the state, the only two things that we've had any interest in fracking is not with gas or oil, because the gas in the mist field doesn't really need hydrofracking. It can be enhanced. So it'd be either for geothermal, for these enhanced geothermal, or it would be if we went back to looking at coalbed methane again. And the state position on either one of those is if they get the proper underground injection permits and they can show us that they're not going to mess up any type of aquifers, then they monitor so they know if there's no offsite impact, then they'll be allowed to do it. Back east, the problem is a little different. Back east, what they're hydrofracking in are in shales to get the gas out of. We don't have, and their issues are many of those shales are very near the surface. They're not like in the geothermal systems where we're saying we're going to drill to 10,000 feet. They're talking much closer to the surface, and therefore there's a higher chance of impacting groundwater.
What are the detriments of mining coal in our local area? What are the detriments to the people, to health, to the land?
For mining coal?
Yes, ma'am.
Well, it'd be the same as anywhere. I mean, coal mining is a dirty business. I mean, of actually pulling it out. You have to be very careful with the safety of it. I'll have to tell you, frankly, I can't imagine anyone would really be wanting to mine the coal here. And it's just because the resource is so small compared to some of these other areas in the United States. But now, that said, if there is interest, with coal mining, I would say the detriments are the safety, making sure that you're extracting, and the environmental impact, and making sure you're reclaiming properly.
I have a question here.
I'll get you in a sec. Yes, yes, sir.
You did a good job of outlining some of the future developments here, and my interest is in the regulatory machinery that's going to have to come into play as some of these new developments come on board. Now, there was a report that came out 10 years ago now by the Oregon Progress Board that essentially said that the state regulatory machinery has been developed for other reasons than what we need today. In other words, they said that measuring ecological conditions, trends, and risk is fundamentally different from the problems that Oregon's environmental machinery was initially established. And resolving these problems will require some new approaches. Now, from your perspective, I'd like to get your thoughts. To my knowledge, there has been no major efforts to update or revise the regulatory mechanisms, whereby, for instance, in your case, how does Dogami interact with fish and wildlife, and with on and on and on. So I'd appreciate your comments. Do you see any efforts on board to update the regulatory machinery, and do you see it as a major problem?
Again, all these are really good questions, and there's never a simple answer. When it comes to regulation, we have a whole how would I say, a cascade of them, starting with federal regulations that we have to maintain and working our way down. So you're looking at, we'll just take a mine site because it's easy. Say we're going to take an aggregate site. Once we get the land use authority, we're responsible for being the main permitter. They're going to write an application to us to get permission to extract that aggregate, and they have to do it to certain conditions that we'll write into it. But they also have to get usually they're going to have to get some type of stormwater monitoring permit from DEQ. They're probably going to have to write an environmental statement after doing an application for NEMS for NOAA. They maybe have to do something with the Corps of Engineers for fish passage. If they need water for the site, then they're going to have to go to Water Resources for a groundwater or a water use permit, etc. I mean, the list goes on and on. What we try to do is get all those entities together whenever we're getting the permit together and going, okay, give us your comments, give us your conditions. We will package it into this one permit. But you can see where that could get a little messy. And I agree, it is, and it takes a lot of time, and it takes a lot of hand-holding by personnel. You've got to really have a staff that's doing that. Now, okay, that's how we're doing it. I don't know what the fix is. I mean, there's two things you could look at. You could put everything under one umbrella and say you've got, you go to one desk and go, here's what I need, and they're going to make it work. And I've not seen that those are particularly useful either. And you'll never get the federal agencies will always have their autonomy. They're not going to go particularly with general contracts. So I guess that's a whole lot of long saying, I don't know exactly how we're going to fix it, and we have more and more conditions that we end up putting in regulation all the time. Now, that said, it is important that we have oversight on a lot of these activities because there's a lot of things that can go wrong.
So I'm going to take one more question in this section, and then I know Vicki's willing to sit around and answer some additional questions if everybody stays seated that has continued. I'm here.
Oh.
Hi. I'm hiding.
Because I was looking for that lady. She had a question. Okay.
So we're going to do one more question in this. If you've got other things and obligations this evening, you're welcome to go after that. Those of you that
I'm
have,
happy to stand around and talk with folks, and no problem.
Before I go to the last question, thank you again to Vicki for coming down here from Portland today. And equally important, thanks to all of you. I know there's a lot of things going on today for making the effort to come out this evening. track it on the college's website to see what's coming up in the future. And again, sign in if you haven't yet.
Thank you for an excellent presentation. You kind of answered my question with the response to this last question. I really wasn't clear on what Dogami does functionally, and so I understand that the department licenses or permits mineral extractions and gas extractions and that kind of thing. Maybe you could speak to some other functions of your department and how you interact with other state agencies.
Right.
I understand, like DEQ would be stormwater and that kind of thing.
Well, and thank you. And I really want to stress, so I have two main programs in the Department of Geology and Mineral Industries. One of them is what we call the Department of Geology. That is our science department. That is the one where you guys down here, when you're working, you're looking at those tsunami evacuation signs, you're downloading the tsunami evacuation maps. That's us. We do that science. We do the hazards. We do the landslide maps. We do the basic geologic mapping of the state. We have all those databases that we've collected over the years on all the data. We compile all of that. It's a basic science, applied science of the geosciences for the benefit of the people of the state and to serve as a policy advisor to the executive. So there's that part. That's the one part. The other part are the mineral industries, and that's what we call, that program is MLRR, and that's the Mineral Lands Regulation and Reclamation. And that, within it, are three main entities. We regulate the operation and proper reclamation for surface mining, and that's all surface mining, although right now that's primarily aggregate, but it could be any other kind of surface mining, for oil and gas exploration, and for geothermal drilling and exploration. So that's right. The entity or someone that's interesting to apply to do that on lands in the state or even federal lands or state lands, if you're going to be involved in that, then you have to get an application. You have to get a permit through us. And then we coordinate our permit with these other entities that may have regulatory oversight. And the difference in that is, again, say, for example, water resources. If you want to get a water right, you have to go to water resources. Now, that water right may involve you actually also getting something from DEQ or the health department. So it's kind of the same thing. So different oversights. And thanks for the chance to say that. I really want everyone to understand we have those two important programs. And most people look at the regulatory part of it because it's the business part. But the other part, the science part, is very important too. So thanks, everyone. I really appreciate it.
And so again, if you have continuing questions, I know Vicki's pleased to answer them for a while.